les travaux de recherche suite à cela sur une séance de questions.
Merci. So welcome everyone. It's my pleasure to present today the work that I've conducted during my thesis, titled Large-Scale Automatic Learning of Autonomous Agent Behavior with Structured Deep Reinforcement Learning. In the last few decades, there have been a number of advances in the field of robotics, with industrial applications such as automated production lines and warehouse logistics, to name a few. However, these applications operate in a very controlled environment, typically use simple sensors and do not operate from RGB cameras, for example. In this thesis, we were looking at vision-based navigation, and in particular, deep reinforcement learning approaches to vision-based navigation. Some of the tasks that we motivate the tasks in this thesis by the following example. So we consider a robotic agent in a 3D environment, and we request this agent to do the following: to find my keys. And so if this agent is in a new environment that it's never encountered before, it might exploit an exploratory strategy that exhaustively explores every room in the environment until it locates the keys. Another approach would be that if the agent is familiar with the environment and has some sort of memory, it could query its memory and then localize the keys and then navigate straight to them. And there is a third example of this, where perhaps the agent has seen many environments that are similar and can exploit structure and regularity of these environments to aid its search strategy. Or, for example, it's seen many examples of homes, and perhaps keys are more likely to be placed in kitchens rather than bathrooms. So it can pick up on semantic cues to aid its exploration of the environment. So there are a number of ways to approach this problem. And traditionally, these were handcrafted and modular. So what I've got here is a spectrum. And on the left, I'll introduce some context of handcrafted approaches, and on the right, end-to-end learning approaches. So a typical handcrafted approach to this problem would be that of simultaneous localization and mapping. And here we estimate the pose of the robotic agent, also constructing a map in parallel. This approach uses classical planning algorithms, and these provide optimality guarantees, which is important, and it can operate with noisy sensors and actions. And another advantage is we can actually visualize the map that's been created by the robot as it explores the environment. However, there are a number of disadvantages. For one, you have to create this handcrafted pipeline, and if you say want to add a new sensor, you would have to adjust and modify your handcrafted pipeline. In addition, typically, this method works with an occupancy grid and doesn't actually understand the concept of keys. It can't navigate to a concept of keys because it doesn't understand it. Typically, you just navigate to an XY location in the environment. And it can also suffer from drift errors in the map construction. At the other end of the spectrum, there are pure learning-based approaches that are trained end-to-end. And in this context of this thesis, this is with reinforcement learning. And this is a general approach that can be applied to a range of problems. And you can learn the semantics and the affordances of objects through interaction and reward. If you define a reward function, that's all you need for your task. And you can train policies that generalize quite well to unseen environments. So you can train on a data set of environments and then transfer that learned policy to a new environment. There are, however, a number of disadvantages. So in general, these are very sample inefficient, and for the vast majority of research, they are trained in simulation. Because they're black or gray box approaches, it's difficult to interpret the parameter, the reasoning process of the agent. You can look at the parameters, but there are so many that it's challenging to interpret why the agent is making decisions for certain actions. And also, this requires a high fidelity simulator. So you may, the agent may learn to exploit bugs or assumptions in the simulator, and that could lead to undesirable behavior. At the other end of the spectrum is semantic slam. So here, researchers have looked to add some learning-based approaches in the SLAM pipeline. And the idea is that you have a semantic classifier as part of the pipeline. And the advantage of this in our context of finding the keys is you can actually identify the keys, and you can find where these have been recognized and navigate to that location in your map. But the disadvantage of this is now you have to expertly annotate your keys, or if you have another object, you have to expertly annotate it, and that may be expensive or time-consuming. And then finally, we reach the area of my PhD. This is structured deep reinforcement learning. And this, again, is a general approach that can be applied to a range of problems, but those problems are narrower than the end-to-end approach. We incorporate structure and priors into our agent architecture based on the problem at hand. And so it's a narrower range of problems. But because of the structure and priors, we improve sample efficiency over end-to-end learning and provide some interpretational aspects of the agent's architecture. But again, there are some disadvantages, like the modular approaches. You have to actually design and craft your architecture. And so just to give a very brief overview of the PhD, we explore model-free deep RL approaches for planning and navigation of mobile robots from monocular input, so RGB cameras mounted on robots, typically in simulation. And our focus is on memory-based agents in a POMDP setting. We look at problems with sparse rewards, so you might rarely get a reward only when you interact with a certain object. And in particular, we're looking at generalization to unseen environments. So we want to see how well our policy transfers to a new environment that the agent has never seen before during training. And so structured deep RL is the particular focus, and the idea is we want to add priors to our agent's architecture and structure the architecture to improve the generalization performance, increase sample efficiency, and be able to have a more interpretable reasoning process. So I mentioned that often we learn in simulation. So why do we learn in simulation? The idea is that this is accessible, it's reproducible. We can share a simulator and a train policy, and someone else can use this the other side of the world, no problem. We can also run parallel training and parallel experiments, and we can run our simulator at faster than real time. And this has a number of advantages from the experimental side. It's easy to generate multimodal data, essentially for free. You can generate RGB data, depth, LiDAR, segmentation, without having to have expensive sensors on your robot. And we are less concerned about safety guarantees, and also you're less concerned about overusing the motors of the real-world robotic agent. So you're less concerned about hardware failure. But the disadvantage of this is it can be challenging to model all the intricacies and details of the real world in your simulation. And that could lead to conclusions not being, you could make a conclusion in the simulator, and this may not transfer to the real world. And there are a vast range of simulators available now. So these can range from game-like environments with corridors and procedurally generated mazes and objects. And this is useful if you want to iterate quickly because they're quite fast to run, but they're not very high fidelity, they're not very realistic. So this is the VisDoom simulator, to be aware of. And it's very easy to generate many different configurations of mazes in this sort of simulator. And then the second example that's become popular in recent years are more photorealistic simulators. And so if you're familiar with this building, this is a 3D scan of the upper floor of our lab. And we've trained an agent to perform point-to-point navigation from one location to another in this simulation of our. And so the problems we work on, we define as partially observable Markov decision processes. And I'll just introduce these, it's relevant for the future slides. So the idea is in a classic MDP, you have a set of states. And so these states in our context might be the wall locations, the pose and location of the agent. You have a set of actions, so this could be move forward 25 centimeters, turn left 10 degrees, turn right 10 degrees. You have the state transitions, the dynamics of the environment. You have a reward function, and this returns a scalar reward at each time step, each interaction in the environment. And this reward function takes as input the current state, the current action, and also the next state. And the reason why this includes the next state is that your actions may be noisy, there may be some stochasticity to them. And so if you request to move forward 25 centimeters, in reality, move 20 centimeters, your reward that you might receive might be different. So this defines overall a typical Markov decision process. And for examples like Go and chess and Atari, these are considered to be Markov decision processes. However, in the real world, we operate in a partial observation of the real world. We don't receive states, and a molecular agent has a camera that's viewing the real world from a certain location. And so you have this idea of an observation function. So this observation function takes the world positions of objects in the agent's frame of reference and performs a perspective projection from the world coordinates to the agent's frame of reference to say as a planar view of the environment. And so by applying this observation function to our state, we get a set of observations for each state. And this problem of partial observability means that there could be scenarios where there are objects that are occluded by walls, etc. And so the agent has to navigate and learn about the world and the objects in it in order to improve its decision-making progress. And in this PhD, we're really focused on memory and partial observability. So this idea of learning about your environment and improving your representation, your internal representation of the environment is important. And I should note that we assume that we don't have access to the states, the state transitions, the reward function, or the observation function. All we have are observations, we can perform actions, and we receive rewards, but we don't have access to these underlying dynamics, the reward functions, or the actual states. And so now I've sort of set the context of structured deep reinforcement learning and the thesis work. I'll summarize some contributions that were made during the thesis. So I'll start with some work where we created a number of benchmark environments and then benchmark these with end-to-end recurrent agents. And then we augmented an agent architecture with a structured memory and metric maps to improve its performance. I'll then move from, these were sort of more game-like environments to more photorealistic environments, where instead of exploring metric maps, we explored graph-based memory, and we decoupled planning from low-level control with a hierarchical approach to planning and navigation. And I'll then cover some other contributions, conclusions, and perspectives. In order to quantify the limitations of an end-to-end approach, we wanted to create tasks, and we created these tasks in a simulator called the Visitor Simulator. And this is the example I showed on a previous slide, which is quite game-like, but it's very easy to generate new tasks and different configurations of tasks. And the idea was these tasks were meant to be proxies for tasks in mobile robotics that test navigation, memory, and generalization. Once we created these tasks, we then benchmarked and quantified the performance of an end-to-end RL agent, and then extended that agent architecture with structure and priors to improve its performance and sample efficiency. So these tasks look as follows. So the idea is that they test different aspects of the agent. So the exploration, can it find objects and return to starting points? It has to navigate and collect certain items and discover correlations in the environment. A rough overview. So once we define these tasks, and the idea is we can procedurally generate these tasks. So we can generate as many of these for a particular task as we want. And what I mean that is the task remains the same, but the wall locations and the item locations might change from one instance of the task to the next. So once we've generated these tasks, we then look to train a recurrent end-to-end agent. And so the agent's architecture is structured as follows. So on the bottom here, we have the agent's input RGB observation. And this is passed through a convolutional neural network to extract a feature embedding. As we want our agent to have memory, we use this an LSTM cell, a long short-term memory cell. And this cell stores from one time step to the next a vector H, which the agent learns to store information about the environment. So this vector H is passed from one time step to the next, and is also used to parameterize the agent's policy, which is a probability distribution over its possible actions, and also the value function, which is an estimate of the discounted return from the environment. So an accumulation of rewards with a discount factor. And so the idea is we receive an observation, passes through the CNN, it's passed through the parameters of the LSTM, and then we sample an action from the policy. We provide this policy back to the simulator, and then we receive the next observation, and the process continues. And by having this hidden state, this 1D vector, we can store information about the environment as we learn and interact in it. And so just to give more detail about one of the tasks, So in this task, it's called K item. And the idea is the agent has to collect 4 items in sequence. And the sequence of items is always the same, but the wall configurations and object locations might change. So here I show the RGB observation, and the agent navigates purely from this observation. I show a top-down map for visualization, but it's not used by the agent, and also the action probabilities of the agent and its rewards and value estimates. So this agent must first collect a green item, and it's never seen this environment before. So it's been trained on a large data set, different environment configurations, but it must navigate first to a green item, then back to the red item it saw at the start of the episode, and then to a gray item, and then back to this blue item later. And this agent has been trained end-to-end with purely reward, and it's a sparse reward, so it only receives a learning signal every time it picks up an object. So eventually it finds this 4th item. So this is relatively good. It can perform the task at hand, but what we're interested in is how well does it generalize, and how many data sets do you need, how many training instances do you need to actually train the agent on in order to get this performance. So the idea is the agent is operating this loop, it's performing actions in the environment and then receiving rewards and its observations. And we can configure this environment with a number of training instances, so a number of wall configurations and item locations. And we vary this from 16 up to 1,024 different instances of the problem. And then we test our train policy on a fixed number of testing environments that's never seen before during training. And so we want to quantify how many environments do we actually need to train on in order to get a good performance in unseen environments. So this is summarized in this plot. And so there are 2 different plots here. The one on the right are the testing scenarios, and the one on the left is the performance of the agent in training scenarios. On the x-axis are the number of interactions the agent has made with the environment. And you probably don't see at the back there, but it's quite enormous. So up at the end, it's 1.2 billion interactions with the environment. And this is really the key crux problem of these approaches. They're really sample inefficient. And this isn't something unusual in the research community. They're known to be really sample inefficient. And on the y-axis, we show the performance of the agent, the average return when we evaluate the agent at different stages during the trial. And then the different colored curves represent experiments we've run, and then for each experiment, we run 3 and take the average and plot standard deviations. We can see if there's a variation in performance between different seeds that we use for instantiating the agent's weights, for example. And so we see, as with a small training set size of say 16, the agent quickly learns to perform well. Right? The agent quickly learns to perform well in the training scenarios. As we move to the testing scenarios, it performs poorly. And as we scale up to, say, 256 and 1,024, we get comparable performance in the testing scenarios. And we actually slightly, I'll say, overfit. So what I mean by overfit is we start to memorize the structure of the layout of the environments rather than having a general policy that can transfer to new environments. But it doesn't seem to be much of an issue. We get comparable performance between 256 and 1,024 in testing scenarios, even if we slightly overfit on 256 in the training scenarios. And so we concluded from this that 256 is probably sufficient for further experiments with more complicated agent architectures. So we have this baseline agent and we want to improve its performance. And so the idea of this PhD is structured deep reinforcement learning. So we wanted to add structure to this approach. And the idea is we want to add some sort of memory. How can we improve the memory of the agent so that it can better perform at these tasks? And so we created this architecture which is called EgoMap. And EgoMap contains a spatially structured hidden state, a metric map. It performs inverse projection of CNN feature vectors. It has a recurrent controller which can query its internal hidden state through self-attention, so a transformer-like read mechanism, and also a global read with a convolutional neuron. And all the operations in EgoMap are differentiable, so you can do end-to-end training with reinforcement learning, and also you can do all the normal RL-related things, so you can discover affordances and semantics through interaction. So there are quite a lot of components in the EcoMap architecture, so I'll step through them one by one. So here I showed it unrolled for two time steps in the environment. So the first step is the agent has its observation, and we need to extract some features with a perception module, a convolutional neural network. And these features still have some screen space coordinates. It's not just a single feature embedding. So each kind of column here corresponds to a patch on the input observation. And what we do with this is that we make an estimate of depth, or we take depth from an oracle like the simulator, and we perform an inverse projection. So we're doing essentially the inverse of our observation function. We're going from screen space back to world space in the agent's frame of reference. And then most of our tasks are planar, so we just discard the height dimension from these coordinates, screen space coordinates to world coordinates, but without the height dimension. We then can map those real-world locations into its hidden state. So they're now located in cells of this metric map. We then parameterize this controller that can then read this metric map with a number of read mechanisms. So these are querying with self-attention and also a global read with a convolutional neural network. And just to give it roughly an idea of how large this hidden state is, it's 32 by 32 in most of our experiments. So it's fairly large, but not enormous. And then from one time step to the next, we perform a differentiable affine transform. So what we do is we take the agent's ego motion, either an estimate or from the simulator, from an oracle, and use that to translate and rotate the map so it's in the agent's frame of reference. And so now we perform this operation. We then repeat the same process again. So we receive our new observation from the simulator. We extract feature vectors with a convolutional neural network, and then perform this inverse projection to map these features into the agent's frame of reference. And again, we have this recurrent controller that can query the map and use it to discover information and use about the environment. And one of the strengths of this approach is that every operation in this pipeline is differential. So later, we might observe an object at time step 0, and it might be this blue object, which actually is the fourth object to collect in the sequence. And we might need to navigate back to it later. And so we store that information in the map, and then 100 time steps later, we navigate back to this object and we receive a reward. And we can then calculate a loss based on that reward, and then backpropagate that loss through all the operations of the EcoMap architecture to update the parameter of the convolutional network that observe this observation of object at time step 0. So we carried out a number of comparisons of this approach. We made a comparison with just a random policy, making random actions. A baseline agent, which is the end-to-end recurrent approach without structure. A neural map, which was the state of the art at the time, which is another structured memory approach, which doesn't include this inverse projection of feature vectors into the agent's frame of reference, and had other limitations, such as the actions were limited to 90-degree turns, whereas in our case, the agent is free to interact and have any turn it wants. And then finally, of course, EcoMap. And we found that this method outperformed these other approaches across our range of scenarios. Another thing we're interested, in addition to the performance improvement between the baseline and EcoMap, is sample efficiency. So trying to improve the number of times we have to interact with the simulator. So I show here the performance of the recurrent approach at 1.2 billion after 1.2 billion interactions. And then we see we achieve a comparable performance with EcoMap with 6 times less interactions with the simulator. So a 6 times increase in sample efficiency. So going in the right direction, but still many, many interactions with the simulator. In addition, we performed some ablations of this approach. We looked at different read mechanisms. So we switched on and off the global read, the attention-based read, and the similarity metric that we were using in our transformer-like read. We found the most important was the global read, so this CNN-based approach, and also the combination of global read and attention-based read does improve the performance. And in addition, so we were taking actions to use for our locomotion estimate, ego motion estimate, from the simulator, and we looked at adding noise to these estimates. So we can imagine we've got a noisy estimate, a noisy sensor that's giving us dubious readings, and we looked at their impact on the performance of the agent. And it seemed to be relatively robust. And what's interesting is when the noise was sufficient, the performance of the ego map architecture reduces to the performance of the baseline agent. So you don't perform worse than the baseline under noisy actuation if you have poor measurements of that noise. And then one of the other strengths of these approaches is that we can actually peer inside the black box, which is the neural network, and visualize some of the agent's reasoning process. So here I show a visualization over several time steps during an episode in the environment. So I show here the RGB observation of the agent, an arrow pointing to the center of mass of its attention distribution, the attention distribution itself, and the three largest principal components of the ego map, so its hidden state. And so what we observe early in this rollout is that there's this blue object, and this object is mapped into the agent's hidden state through this inverse projective transform. And this is actually the fourth object the agent needs to collect in this scenario. And much later in the rollout, so it's time step 100 time steps later, the agent is about to collect this gray box, and this is actually the third object to collect in the sequence. So it's about to need to return back to this blue object. And what we observe is that after this agent picks up the object, it's now querying for the location of the next object. So you see that there's a peak in the attention distribution, and that corresponds to the location of this blue object. And the agent continues querying for this object as it navigates back to it. So here we see the same object again, but it's partially occluded by a wall. And so we're still seeing it being attended to. But what I found really interesting is that once the agent gets around the corner and observes this object, it stops attending for it. So it doesn't need to attend it because the object's in its field of view, and so it doesn't choose to query for it. I thought that was a very interesting observation about this the agent's reasoning process. So we then move to more photorealistic environments. These environments, the game-like environments, are very simple. They're very useful for creating new tasks, new scenarios, but we were looking more to think about transfer to the real world. So we moved to a more photorealistic environment. And in particular, now instead of thinking about metric maps, we're looking more at graph-based memory. How can we include this as part of our agent's architecture? And in the end, we decoupled planning from navigation. So we had a high-level planner that was using a graph, and a low-level controller that was doing waypoint-to-waypoint navigation on this graph. So as I mentioned, we addressed the problem of planning and control in photorealistic 3D environments. And here we explore the implementation of a neural path planning algorithm. And this algorithm operates on uncertain or incomplete graphs to perform hierarchical planning and control. And the task we consider is image-conditioned goal navigation. So this is different from the tasks I presented previously. So in this case, the agent receives its observation, and this is passed through a CNN, but in addition, it receives a goal image. And this goal image corresponds to a location in the environment where the agent needs to navigate to. And when it reaches this goal image, the episode resets, and it's given a new, it's moved to another location, and it's given a new goal image to navigate to. Other than that, a baseline end-to-end approach, the architecture is very similar. So you just concatenate these two input features and then perform the normal LSTM-based planning and navigation. But we wanted to augment our agent with some sort of graph-based memory. So the idea is we want to incorporate a graph mechanism in the agent's architecture. And I mentioned this operates on uncertain or incomplete graphs. So I just want to give some context about what I mean by that, because often I'm asked the question about it. So here I show a typical graph, and all the connectivity is known, and we want to perform shortest path planning from this node to the target node. And there are many algorithms available for doing this, and they're optimal given all this information. And so this is the optimal path from the optimal shortest path from the source to the target. In our case, we consider graphs where we don't actually have the edges. We just have nodes, and we want to still perform some sort of planning. So we have some other information available, and that is that for each node, we have an RGB observation of the agent from a direction in the environment. And for these RGB observations, we can extract feature embeddings, node features. And then for each pair of nodes, we estimate the connectivity with a neural network that we train, of course. And so this takes us into 2 observations and the hidden state of the agent. I'll elaborate in a few slides more about this function that we learn. And so we can perform estimates of connectivity between different nodes, and then we can build up a graph by doing the product of all the different combinations of nodes in the scene. And obviously these estimates aren't perfect. They contain false positives and false negatives. And if you want to perform shortest path planning on this graph, you can't do it with a classical algorithm because you only have these estimates of connectivity which are between 0 and 1. They're just what the neural network considers the connectivity to be. So you could, for example, threshold these probabilities and then perform classical planning. And so then you would have binary connectivity, but the path you would get would not correspond to the optimal, may not correspond to the optimal one. And you also don't exploit this visual information. So we have these rich visual observations. Here you show there's a lot of free space in this corridor, for example, and you don't exploit this if you were to just threshold the connectivities. And so our neural planning approach exploits these uncertain connectivities by using the visual features, and it can also learn from regularities in the graph structure, such as if I have a nearby neighbor who is very confident about connection to a node, I can probably be more confident about my connection to the node, even if the estimate I have is of low confidence. So in order to generate these graphs, we had to create a data set. And in order to do this, we learned an exploratory policy, and we learned this with deep reinforcement learning. So proximal policy optimization is the algorithm that we used. And while we were learning this policy, we also learned this parameterized function for linkage prediction. And so this was taking samples from a trajectory of observations and also conditioning on the agent's hidden state, because it should be that as the agent explores the environment, you can be more confident about connectivity between 2 observations by conditioning on that hidden state. And then we perform a joint optimization of the RL objective and the linkage prediction function. And then once we've trained this exploratory agent, and I should mention the reward we use is a coverage-based reward, we can then generate a data set by rolling out this agent in the training environments it's trained on and also a set of validation environments. So the idea is we have 72 training environments, and we can generate, we generated 1,000 graphs per environment. And if you take the product of all the combinations of start and endpoint for each graph, there are about 1,000 problem instances per graph. So you end up with like 72 million problem instances in the training environments, and then 16 million problem instances in the validation environments. And these graphs contain the following information. So the distance between nodes in this E matrix, the estimated connectivity from one node to another in this E matrix, the visual features for a particular node in the matrix V, and also we have some ground truth information that we can get from the Oracle, from a simulator. And the idea is we're going to use this ground truth information to train a neural approximation to a path planner. But when we evaluate it in these validation environments, we just use our neural approximation. We don't have the ground truth available. And so this ground truth information is obviously the ground truth connectivity, and also a matrix which contains the next path in an optimal path from one node to a particular node in the environment. And so we explored a graph neural network approach to this problem, and the idea is that we treated planning as a classification problem. So we have a graph, and for each node, we're going to perform for example, if the graph was 32 nodes, we could perform a 32-way classification over the next node on the optimal path to the target. So there's a sequence of links to take, and for each node, we're predicting the next link I need to take in the graph. And for each node, we have a feature embedding X, and this X is a combination of visual features, the edge connectivities, a Boolean indicator, which indicates whether that node is the target or not, the Euclidean distance of that node to all the other nodes, and also this S vector, which is a one hot vector, which indicates which node I am on the graph. So the node can then refer to which node it is on the graph. And the approach we finally explored was a graph neural network and long short-term memory approach. And the idea is that if, for example, in this simple three-node graph, at each time step, we perform several iterations, and at one iteration, each node performs message passing to its neighbors. So in this case, there are three nodes, so this node would receive three messages. And then we wanted to somehow integrate these messages. And so there are many ways to do that. You could use an MLP, for example, but we explored a few different ablations, and we found an LSTM-based approach that iterates and accumulates over these messages, outperformed other approaches. And we continue this process of message passing and recurrent updates for a number of iterations. And then we perform our classification. We compare this approach against two handcrafted methods. So one of these methods is a classical planning algorithm, Dijkstra. And in this case, we threshold the probabilities. So we take our estimates and we threshold them at different values, and then we evaluate the performance on our validation set of a classical algorithm. And the second is Dijkstra with a custom cost function. And this custom cost function mixes together distance with a weighting of the log probability of the estimates of connectivities. And we vary this weighting to evaluate the performance again on the validation data. So we compare against two metrics for this planner, this high-level approach. One is accuracy, so how well we're predicting the next node on the path to the target compared to the ground truth, and also HSPL. So it's sort of a comparison between the path that you predict and the optimal path. So it's success weighted by path length, and we compare against these two symbolic approaches. And we show here two different ablations of our neural approximation. And in one case, we include the visual features, and in the other case, we don't even include the visual features. So the visual features are used to estimate the connectivity, but the graph neural network doesn't have access to them. And what's quite interesting is actually you get quite comparable performance between these two approaches, even without the visual features. And so there are some regularities in the graph structure which can be picked up by the graph neural network, which are not usable by a classical planning algorithm. We also compared providing as input the ground truth. So in this case, the graph neural network approximation has everything it needs to perform actual classical planning, and we compare that obviously to a classical planner. The classical planner is going to outperform it, but the question is, how close can we get to classical planning given all the information that a classical planner has for planning? And we're still not as good. Maybe we could do better with a bit more tuning, but we're quite comparable in terms of the comparison of the path we found to the optimal path. So that's this 0.983. In addition, we carried out a number of architecture ablations. So in this particular ablation, there's a way we can accumulate and iterate over the messages that have been passed each iteration. And this could be with, for example, a multi-layer perceptron. You just chuck everything into an MLP and you use that to accumulate your messages, or an LSTM. And so we showed that here in orange, the LSTM outperforms the MLP by a large margin, and even in a larger data regime. So here I'm showing the scaling of the dataset size, and you can't even catch up in a large data regime. So it was quite important to add this structure to our network architecture. So this is great. We now have this neural path planner, and we want to then interact with it and use it in our simulator. But this planner outputs points to locate to. It doesn't actually interact, and it doesn't output the low-level actions. So the idea is then we couple our high-level planner with a low-level policy that's been trained to perform point-to-point navigation. So the graph planner is provided position estimates by the low-level policy, and it's outputting the next node the low-level policy needs to navigate to in the environment. So here I show an evaluation of this hierarchical approach to planning and navigation in a photorealistic environment. So the agent is navigating from this green source node to a red target node. And at each time step, at each interaction with the environment, the agent is replanning on the fly using this graph neural network approach. And then here I show a failure case, actually. So in this case, the agent is trying to navigate to the other side of this wall, and there's a mirror in front of it. And you could consider that perhaps this mirror confuses the agent because it thinks it's free space when it isn't. And what we observe actually is that the local policy seems to overcome this issue. So the coupling of this high-level planning with the local policy, somehow it sort of can shake itself out of a local minimum. So now we've got this combined approach. We compared it to other methods. So we're not talking about just the planner now, it's the planner with the low-level control. So we compared against a graph oracle, which is providing the optimal goals to navigate to. And so the idea of this is to test the performance of just the low-level controller. We compared against a random approach, a recurrent end-to-end approach, the two symbolic approaches, and then two instantiations of our neural planning algorithm. And we achieved pretty good performance. Now I've covered some of the main contributions during my thesis. I'll just briefly cover two other contributions that I made recently, then some conclusions and some perspectives. So some of the other contributions that were made during this thesis are more related to RL applications in video games. And so I had the opportunity to perform a 6-month internship at Ubisoft's research and R&D department. And there I was working on deep RL approaches for navigation and planning in video games. And this is quite good because you're not worried about transfer to the real world. You're already in the environment you want to actually roll out your policy in. So that has one advantage. And we were looking at point-to-point navigation in video games. And video games come with other challenges. They're very complex action spaces like jumping, double jumping, sometimes teleporting. You have jump pads that can bounce around. And also the environments are much larger. So the environment I show here, if you mapped it to a real world environment, is 3 kilometers by 3 kilometers by, I don't know, 500 meters. It's vast, procedurally generated. And in this case, we explored a hybrid graph and RL-based approach to this problem. And then the second contribution I made is something called Godot RL agents. And this is an RL interface for a game engine. So at Ubisoft, we're using something called Unity ML agents, which is great, but it's not really open source. And so I wanted to make an alternative. And this is an example where you can build different environments in 3D and 2D and perform reward-based learning. And this could be for making games or testing research hypotheses, things like that. It includes a number of sensors like LiDAR-based sensors, virtual cameras, and other sensors. And you can perform parallel training, so you can have many agents that learn in these environments through interaction. And I provide a number of wrappers for this to standard RL algorithms. So I didn't implement any algorithms here. I just implement this interface with its game engine, and then many examples in the game engine and custom sensors. And I'm currently looking to extend this with multi-agent work. And yeah, as I mentioned, you can run parallel training, so many agents running in parallel within the game engine, and that speeds up the time it takes to train an agent. So just to summarize with some conclusions, so I've been presenting about structured deep reinforcement learning, and the idea is to improve generalization performance, increase sample efficiency, and provide more interpretable reasoning processes by adding structure and priors to the agent's reasoning process. So we did this we demonstrated this by building environments and benchmarking deep RL agents in these memory-based tasks. Once we quantified their performance and their limitations, we extended the performance of an end-to-end approach with metric maps and inverse projective geometry. And then I show this learning to plan approach where we have this high-level graph neural approximation of a path planning algorithm, and then a low-level planner that actually interacts with a simulator. So these correspond to 3 conference papers. So that's the top row, that's what I mainly presented today. And then these 2 things related to video games are workshop papers that I recently accepted at the AAAI workshop on RL and games. Of course, work always continues. So in terms of research perspectives and things to do from now going forward, I think there's some interesting work related to transfer from simulation to reality. And so there have been a number of works looking at this for end-to-end approaches, but there is limited research conducted on the transfer of these structured representations to the real world. Also, the addition of auxiliary or self-supervised losses is something of great interest to me and to improve sample efficiency. So there have been works in RL for this, and there's actually a recent extension of the ego map architecture which adds auxiliary losses and improves performance and sample efficiency by doing so. I'm also quite interested in attention-based models. So we've seen how transformers have revolutionized the domain of NLP, and there's been limited research on this in the field of deep reinforcement learning. And so I think those sort of based models are very powerful, and I think there could be a lot of fruitful work could be conducted in RL on those. And then finally, multimodal applications. So environments which combine text and vision, I think are very interesting, particularly if the task is defined in text. Because then you could, if you train it over an ensemble of tasks, you could perhaps transfer to a new task that's not within your data set because your task is defined as text. Generalization to new tasks, I think is very interesting. And there have been some works on this already. There's this recent Excel land environment where you can perform these sort of approaches. But I think it's just the beginning of this sort of work. Now, I thank you for your attention today, and I welcome any questions.
Thank you. Thank you. Around 45 minutes. That's perfect. Congrats. So, as usual, it's time for questions. So, I will start with Elisa from the University of Rennes.
Thank you, Mr. President. Okay, so thank you, Edward, for this very, very nice presentation. Very clear, very well illustrated. And so with your documents, the manuscripts, it's really nice. It was a pleasure to read. It was very difficult to read for me, but not because it was badly written, because it's not. It's really well written, but because it's dense. It's dense in the sense that it's very impressive the amount of
He's just put the two numbers.
Yeah, it's quite impressive the amount of very difficult pieces of related work that you had to assemble, and it's very creative in the way you did it. It's really impressive. I was, but well, at some point I was like, okay, this is never gonna work. Of course it does, but somehow, yeah, I thought it was quite magical that things, for example, what you're doing with your ego map and the modules, that they actually work together. Well, I was very impressed. So thanks for that. It was I learned a lot, and well, I was very happy about that. On the few negative points, I think I found it out in the report, so I'm not going to say it again. So you have two types of contributions in your thesis. The two main contributions that you presented, and then you have all the environment that you did. And so this is, I'm going to start with that probably, because it takes half of the thesis and the document, and also it was a bit difficult for me. So I understand why you presented them like that. So you start with the wisdom and environment, and then you at the end we continue with the two last contributions that you gave. So the one that you did at Ubisoft, and then the other one that you the Bodo reinforcement learning environment. And yeah, so please, if I want to start working in this field, and I understand that you needed to set up new environment to actually show that structured reinforcement learning is useful. and the standard environment don't really help you to show that. And for many reasons that you will explain at the beginning about the fact that it's better to have simulation on your environment because you need a lot of sample to learn your policies and everything. But so can you give me a kind of high level overview of why should I use one before instead of the other, and where should I start if I want to start working in this field?
So I think it's all about what your end goal is at the end of the day. If you're interested in transfer to the real world, there are environments like Habitat. You use scans of real world buildings to train them. It makes sense to use those. So you can simulate a real world camera in this environment, and you can train with it, and then transfer to the real world idea. And there's, as I mentioned, there's been works that do that. If you're interested in more fundamental research about memory and generalization, and you want to be very controlled about the environments you use, because you can scan real world buildings, but you're always going to be limited by however many you can scan. And often you'll find, for example, in Habitat, the scans are quite luxurious. So they're buildings that are very, very nice looking. And it makes sense because a lot of them, they come from estate agents scans. It's originally the software they used. Scanning this was from estate agents. And that is really not actually aligned with the real world. And so leads to a number of problems. And if you're just focusing on, say, memory, maybe the tasks available in Habitat are not so suitable. And you might want to use, I don't know, Vizdoom, or Vizdoom's a bit old now. People are more interested in DeepMind Lab or testing memory-based tasks, although it is much slower than Vizdoom. So that's one of the main reasons we didn't choose that. We want to experiment as quickly as possible. There have been recent works to XLand environment that was created by DeepMind, but they haven't shared the environment. So and that's a real shame for the community that they're on, people putting out there these environments. So that's something that needs to be more community focused, and that they're in. And so to summarize, it depends on the task at hand that you want to perform. If it's simulation to real, Habitat is the number one thing.
Habitat is for the last contribution.
No, it's for the topological memory. So the neural path planner is in Habitat.
Okay, so not one of the environment you proposed.
No. What do you mean by the I'm confused by
So you propose three types of new environments for structured deep reinforcement learning, right? The first one with using the Vizdoom thing, and the Vizdoom environment, sorry, and then the two last ones that you presented.
Yes, so there's Vizdoom. I use Vizdoom.
Yeah.
And then the second one is Habitat. So Habitat was created by Facebook AI Research, or Mentor, whatever it is now.
Okay.
And it's a great tool. It's a fantastic tool for community, and actually it loads data sets that are already available in the community. So it kind of tries to subsume different simulators into one.
Yeah, but this one is not from you, right?
No, that's not from me.
Okay.
And so the next one that we made at Ubisoft, that is available, is we open source the environment, and that's more focused on video games. So if your end goal is to research to multiplayer video games, that's a very suitable environment.
But it's not possible to, okay, Doom is also a video game. I understand that this was not, so the idea with this Doom thing is that it's light, it's fast, so you can do a lot of things with that. So you would do kind of proof of concepts with your RL
So
architecture.
that's more the objective of the Godot RL entrance. The last one, it's very easy to iterate and build an environment. I can build an environment in a day to test a problem. I'm obviously very familiar with it, but it's quite easy to pick up, and there's many tutorials for making games in it, so you can easily follow one of those and build an environment and interact with it with RL.
Okay, but then if I have the last one, the Godot environment, I can just forget the first one, the one that you did using the Vizdoom environment, or what?
Well, it depends, because there are many benchmarks available for this too, which aren't available in this new one. So if you want to compare against other state-of-the-art approaches, it'd be better to use Vizdoom all the benchmarks that we created, the scenarios we created for Beeching, because there's already standard benchmarks available that are being published. And you can say, okay, we compare against the performance of these other approaches in a consistent environment. So people are more familiar with it, but perhaps if it gets traction, that might be the case with good RL agents. But the environments have provided demonstrations. They're not meant to be used for benchmarking. The idea is that you, as a video game creator, can implement a prototype of your game in this to test different hypotheses in. And there are already other companies that are doing it. There's a company called Airlab that's using it to build tests for video games. Part of my work in my new job, my new role, is to extend this to other scenarios. And, yeah. So anyway, that's another.
Okay. So now I understand better. It was a bit confusing. How they fit together, all those environment that you put. But
Yeah. So to summarize, yes. So
yeah.
the real reason I made that last tool is because at Unity, at Unisoft, they were using Unity ML and it's not free and it's not open source. You can't actually change the protocols used to interact with the simulator, for example, to send stuff over and over. And it's actually quite, when you want to do something a bit more exotic, you can't actually do it. So it's okay, I'll make a tool that you can do the same sort of things. It's not as fully featured yet as the Unity ML agents, but that's the idea of this tool, to provide an open source equivalent.
Okay. So I have a question about chapter 4 and chapter 5, but actually I'm going to make a transition with this. So the environment at Ubisoft, one that is based on Unity, why didn't you use your methods? So the neural path planning algorithm that you proposed, why didn't you use it directly in this environment?
It's mainly to do with how quickly you can generate an estimate of connectivity. And so in video games, they require you to make a decision every spin 60 times a second, and you might have 100 parallel agents that you need to make decisions for. So they need the inference time to be really, really fast. And if you have a graph neural network that's to run to pass messages between nodes, and in the photorealistic neural path planner example, the graphs are very small, they're like 32 nodes. In these other approaches, it was like 1,600 nodes, but they're absolutely enormous. In the large example I showed there, I think the biggest graph was 3,200 nodes. So then you've got the product of all those, so it ends up being like a million different edges that you've got to estimate over, and then you've got to run that in real time. So it's not possible.
So it doesn't scale.
It doesn't scale.
Okay, I think that would have been nice also in your document. That's from time to time you just come back to what you've done before and say, okay, and if I would have used the method I've developed in the previous chapter there, well, it was not obvious also why you didn't use it. I understand it's a scaling problem, but I think you should have made it clearer.
The other reason was that in video games, you can actually run you can roll out the agent. You can say, okay, I've got these two nodes. Can you offline? I'm just going to roll you out and calculate the connectivity. Whereas in a real world robotic application, you can't do that. You can spawn an imaginary robot that does your connectivity estimate. That's the advantage of this approach. You can't get that line or in real time while you're doing something else.
Yeah. Okay. Okay, so let's come back to your two main contributions. So first, Eagle Map. So as I said, so I understand that it works. So you have only one LSTM cell here.
Yeah, it's not a stacked LSTM. It's just a single LSTM. Well, with not one LSTM cell, it's a hidden size of, I think, 256 or something.
Yeah, okay, it's because the size of the hidden state is huge. Well, it's not that huge, but you said it was 32 times 32, right?
So the map itself, the map itself is 32 by 32, sort of height and width. So that's whatever thousands vectors that are being stored in it.
Yeah, okay. And so you explained that because you're a planner, you can remove one dimension, right? You don't so it's not a 3D projection that you do.
Yeah, so the third dimension of this tensor map is the feature dimension of the feature vectors extracted from the CNN.
Yeah. Yeah. So can you go to which one is it? So it's the one where you show the explanations. You look at
The visualization.
Yeah, the visualization. So as you know, this is 44. Yes. So this one is it's even more magical for me. So okay. So I understood better during your presentation. Actually, there are a few things that I really understood better during your presentation. So one of them is because, in fact, the reason why you so first, those are the principal components of what, and why three principal components?
So as I mentioned, the feature vectors out from the CNN have a certain dimension.
Yeah.
I think it's also 32, but it's quite confusing. Let's imagine it's 64, so it's very confusing. And obviously, if you want to visualize all of those, it's very difficult. So I calculated many rollouts of my agent running the ego map. I then took all those feature vectors and I calculated their three largest principal components, and I put those to this new rollout. So the new rollout, I take each cell, I extract the three largest. Well, I've already calculated the transform to extract the three.
The reason why you were able to say that this is where I saw the blue object and this is where he queries the blue object is because there is a spatial coherence in your perception module and in the map, right? So you are able to say I was there in the maze, and it was looking at that. So this is the blue object. This is the blue and white, right?
So every time step I translate and rotate the maps, it's always in my frame of reference.
Yeah.
So I turn and it turns with me, and I form my mapping in the new map in my frame of reference. So yeah, there really spatial relation between where the map is relative to me and objects that map.
Okay. Because this is a booming field, right? Well, you may not know, but so people are trying to find a good way to explain what deep neural and complex deep neural architecture are doing and what they are actually learning. And I think this is great because, well, there are a number of things that makes it easier for you. First, that okay, you know where you have some kind of expert knowledge about your environment. Well, you have an expert knowledge. You know how the environment look like. You know where the things are located, and you have a correspondence, direct correspondence between the architecture and the environment. But I think this is a. I was a bit, let's say, I thought that your perspective were a bit lacking ambition compared to what you did during your thesis. You were talking about losses, transfer, which is okay, but well, and the few things that are a bit obvious in the end, going for transformer, which is okay also, but I mean, what you're using is already amazing. So okay, it might work better, but it's gonna be and I think what you're doing can open a lot of well, help other research fields, because what you're doing is basically you're that's what you said at the beginning. You're including a priori background knowledge into your architecture. And I think this is huge because this is actually working. And after that, you can actually use the fact that what you have constrained is actually it has a semantic, and you can look at what the architecture is showing you, and it gives you a lot of feedback about the words, and I think this is really great. And well, yeah, I would tell you to okay?
No.
Yeah. Just look at so if you feel like continuing working on that and developing what you've been doing, look at the field of explainable reinforcement learning, which is, I mean, there are very few things in this area, and this would be, I think, a great contribution.
Mhm.
And so for your chapter 5. So chapter 5 is about your neural path planning. So here I was surprised, I think, but then I understood during your presentation, is the fact that at the end you showed that so you estimate with your neural network the connections between points, and then what I didn't understand while reading, but it was written, but I didn't understand at that moment, is that you estimate the connection through the features, and then you reuse the features again as labels on your points to navigate. And it's quite interesting because you show that in fact the features are not that useful anymore, that the connections, the information that you have, the estimates are much more useful to navigate, but this is quite normal because in fact the features are already included into the connections, right? So when you say I don't use them, and you show the table, I don't put the slides. When you show the table where you say, okay, I have done this with or without the feature information, in fact, it's quite normal that. So I was surprised that you didn't really need those feature information. It made the system work better, but not that better. But in fact, it's already included.
I was kind of surprised by that bit. I guess in some respects it makes sense, but I didn't expect it to be so close. It's interesting.
No, but I think the reason is just that. So what I found counterintuitive is, for example, as a human or as an animal, I think you would just look at some place, recognize what is there, and regardless of whether you can actually go there, if you see it in your sight, then you would try to go there because this is, for example, your goal or close to your goal or whatever. So I thought, okay, this is very strange that it's actually not really using that. But the thing is, to estimate that there is a connection, it's because of the similarity between the frames, right? And so this is already taken into account. So actually, the fact that there is a connection means that you're close to your goal, or you're close to the next goal in your path.
Mm.
Yeah. So I had a revelation when you were showing that. Okay, so I think I will stop here. So thanks again for everything and for this great presentation.
Thanks for your questions.
Merci Lisa. So I think it's time for giving the floor to the second reviewer. So David Filia, within Visio. I think David, you hear us?
Yes. Do you hear me?
Yes. David.
Can I show David?
Yes. Oh, we see you.
I can see myself with a lag. Okay.
I don't hear very well the sound, so I'm just gonna. It's okay.
Yes. Do you hear me well?
Brilliant. Thanks.
Okay. Thank you. I would like first to congratulate you for the quality of the manuscript. As Elisa said before, it was a pleasure to read. It was very nice, well illustrated, and I learned a lot also on what you did and all these contributions to reinforcement learning and putting structure in the networks for reinforcement learning. I would also like to thank your supervisors for inviting me and for having discussion through the thesis. It was nice to follow your work and see where it leads today. So I have a lot of questions. In fact, some are small technical questions, and some are broader. Maybe a first question, which is a bit technical, but also a bit far-reaching. It's on the sensors you are using. You make a lot of discussion about using vision, and you make works using vision, but you also use the distance sensor. And in robotics, we like distance sensor a lot because it makes it easier to find ways and avoid obstacles. So, what would be your view on that? What is your, well, at the end of your PhD, what do you think of that? Should we focus mostly on vision? Should we use distance? Should we use both? Maybe, obviously.
By distance, you mean LiDAR, I presume?
Yes, LiDAR, depth camera. I think.
So I think if you're not worried about cost constraints, why not use LiDAR? It's probably more robust. I don't know, there might be issues with I think if you're not limited by cost, why not use LiDAR? But I think cameras are much more cheaply and ubiquitously available. So you see that in autonomous vehicles, there are different approaches. For example, Tesla try to navigate purely with cameras. And that's because it's cheaper, I think, is their main reason. Or they think they can do it with just cameras. So in robotics, I guess it really depends on your end application. But in the long term, it's going to amount to cost. And so if you can make a cheaper robot that uses a camera instead of LiDAR and you can get comparable performance, it would make sense to use cameras. Obviously, LiDAR has many advantages. Particularly, you can get a depth estimate from all around you, which is more hard to do. You need a panoramic camera to do something similar. So it's a bit kind of, it's not either one might be useful depending on the use case and the cost. Certainly in video games, like the work I was doing at Ubisoft, they use something called raycasts, which are very similar to LiDAR. You can make a measurement of depth in a certain direction, and they're much faster to run in real, on your machine in real time compared to rendering an RGB observation. So they don't use RGB measurements at all. So again, it depends on the use case.
Yeah, but clearly in robotics, probably using distance is also interesting as you did in video games. So you can use stereo camera if you don't want to pay the cost for LiDAR. But...
I guess that there could be another instance where you learn using many modalities to get your expert policy. And then you do imitation learning on that expert policy with just the RGB camera. And that could be an interesting application as well.
Yeah, clearly, that could be a good one. Okay, so I really liked all your contribution about evaluation, environment evaluation. So there's been a discussion on it already. I just have a few technical questions about your first contribution. So the idea of using an old-fashioned 3D engine to make things faster is obviously a good idea. I had students spending their life waiting for results for reinforcement learning in simulator. So I think it's good to have something that can go faster. You defined a few several tasks, and there is one which is called two-color correlation. And in the task there is a complexity level. I did not really understood what was this complexity level. You talked about the number of rows, something like that, but it's not clearly related to the number you gave in tables.
Yeah, so the idea is we wanted to make the scenario more difficult, and how we did this was actually just having more complex mazes. So essentially we construct a maze which is, I think the right term is complete, and then we randomly remove a proportion of the walls, and the complexity level controls how much of the walls we randomly remove. So it's more lower complexity, we'd be removing more of the walls randomly. So it's purely that, and I maybe didn't explain it very well in my manuscript.
Yeah, no, it's just a technical detail. In the table, you gave a complexity level 1, 3, 5, something like that. But it's related to probability of removing wall behind someone.
Yeah, so I think 5 is 50% of the walls are removed, and 1 is 90% of the walls are removed. So it's like the fraction, the fraction that remain, something like that.
Okay, and I was wondering in the results you presented it was slide 23. There is an upper bound performance, and you are not completely reaching it. Is it possible to reach it with say a behavior like that, or is there some additional information in the upper bound that cannot be used?
I think actually that there's no policy that could do it, because this makes an assumption that the agent takes one step and then immediately solves the task. And so in this scenario, it's a labyrinth-based scenario, so the agent must find an object. So it's like the agent spawns in front of the object and takes one step and immediately gets one result. And the reason why you can never achieve this is that every step there's a small negative reward to encourage the agent to complete the task quickly. And so if you can interact with 10 time steps, you're going to get 10 of these negative rewards. So I actually think that the blue curve is the best performance we get in this task. On the left, of course.
Okay, thank you. So now on the contribution on ego map. So in the drawings and in what you explain, you have this ego map. So it's from the point of view of the agent, and when you have an action, you move the map. And you explain in the manuscript that it's introducing errors, which is completely true, and that you resort to a global map, to a global storage of a map. I don't remember the words exactly. And it's a contradictory with what you say and show. So can you explain again what is this idea of storing a global map, and how do you go from the global map to the view of the agent?
Okay, I'll just briefly explain why we need to do that in the first place. And the idea is that every time you apply this affine transform, there is some loss of information. You're essentially applying some sort of low-cut filter to your high-cut filter, some sort of filter to your map. And if you apply this even for 20 time steps, you smear out, you lose much of the information in your map. And this is a real issue. So what we did is the map itself is stored in an allocentric frame of reference, so a global frame of reference. And then when the agent projects its features, we project them in its frame of reference, and then we transfer that to the world frame and store them. And when the agent reads the map, or the recurrent controller reads the map, we then transform the global map into the agent's frame of reference. And so this avoids this issue of kind of smearing out information through repeated affine transforms. I think.
And doing this, you assume that you have a position of the agent, in fact, that the odometry, you use the odometry as a reference, or is there a mechanism to update the odometry from the other data doing SLAM?
Yeah, so in this case, we assume that there's an oracle that can provide us either the ground truth ego motion or an estimate of it with a noisy sensor. So that's why later I show an ablation where we add noise to the estimates. But yeah, we make this assumption. And there's another assumption we make, which I think is worse, and that is that we assume we have depth or a prediction of depth, which is quite good. And in most of these examples, I'm using the oracle. And clearly, in the real world, you don't have that. And so I think that's the real limitation of this approach. It'd be better to be predicting depth and learning to predict depth as you simultaneously learn this architecture, and then using the predictions. And obviously that would have an impact on the performance as well. But that's not what was undertaken in this study.
Yeah, okay. I see. And so yeah, there is this problem of projecting to the real position using depth. But for the position, do you think you could upgrade your architecture simply to perform some correction of the odometry, for example, basically doing SLAM, not assuming the non-position?
Yeah, so you could imagine that you could have an additional output of the controller that was performing a sort of regression of your rotation and movement, or maybe estimating the error on your position estimate. So you could imagine it estimates the delta between your real movement and whatever's coming from your noisy sensor. So yeah, you could consider that as like an auxiliary output of this model.
Yeah, I agree. I don't think it's much more difficult than what you have already done. Okay, so your evaluations show that it's working very nicely. I think you did not show the performance on the last task, which is two-color correlation, if I remember correctly. Why don't you show the performance? Is it not working at all, or is it not interesting?
From memory, I'm not sure why. I think we were more interested in these item-based tasks because often you need to discover where an object is located and then navigate back to it. Whereas in the color correlation scenario, there's a totem in the middle of the map, which could either be red or green. And if the totem is green, you have to collect green objects. And if the totem is red, you have to collect red objects. Sort of correlation between the color of the objects and the totem is why it's called that. And from memory, I do not know. I don't know the answer to your question. I don't know if it was. I'm not even sure we evaluated it on that particular task. I know that we created that for a benchmarking paper when we created the Visdoom scenarios, and I think when we went to the EgoMap extension, we thought, okay, these item-based scenarios are the most appropriate for this architecture because they really require memory. And in the case of this totem-based scenario, as soon as the agent observes that object, and there's some visualizations in the paper, I believe, that show it stores in its hidden state the fact that that's the task it's working on.
Yeah,
and then
you don't really.
Yeah, exactly.
Sure. So using this ego map, as we already discussed, is an interesting way to provide interpretability and to behavior of a network. So what you show is interesting. You perform a dimension reduction for the ego map. I don't remember what is the size of the feature vector in the ego map that you use in your experiment.
From memory, it's 32.
Okay. Did you try with smaller dimension? Because one of the possible advantage of that would be to force some interpretability. For example, if you just have 4 dimension, it would need to store the 4 object in the 4 dimension or something like that.
We did not, and that's because the ego map architecture, if I go to the right slide, if you remove the parts with the map and the fact you're doing reads with the controller, the architecture matches the baseline recurrent end-to-end agent. So we kept every other parameter fixed to be comparable with the end-to-end agent. So that's the reason why we didn't explore a smaller size.
Yeah, sure. No, I was thinking about the feature dimension behavior. So you keep the same spatial resolution, but you reduce the number of feature maps.
Yes, so obviously the feature size is the size of this output of the perception module, one of those columns, and that's obviously, as I mentioned, 32, and that's comparable with the baseline. So
okay, so I didn't understand. Okay, and for the analysis of the behavior, so you showed that the memory is storing some information, but do you analyze also the behavior of the agent using the ego map? For example, when it needs to go back to a position, is it able to go with using the shortest path, for example? Or is it more like using a replay of a path? Or, well, basically, do you have a possibility to analyze if it's doing computation or planning, for example, in the map, or if it's mostly reusing memory?
That's an interesting question, and we didn't perform any analysis of that. It's interesting because there's like value iteration networks that do something quite similar with sort of maps like this. So it's an interesting question. We didn't perform any analysis of whether it's performing shortest path planning or some sort of planning algorithm inside the calculation. I would think, but I guess, yeah, the global read maybe could do something like that, but it's quite a small convolutional neural network. It's only 3 layers, so I don't think you'd have enough depth to perform planning. If you were going sort of any more than 3 steps, 3 cells in the map, you wouldn't be able to perform an approximation of planning with the global read. So intuitively, I'd say probably it's not doing that, but we didn't run any experiments or analysis to look into it.
Thank you. So on the next contribution about using a topological map, so once again, I really like the idea. So a small technical question first. So you use RNN for the message passing algorithm, and you argue that you need to compute a mean and an argmin in the process. I did not check, but is it in theory possible to implement a mean algorithm, a mean function using a recurrent neural network?
Yeah, well, argmin, min yes, and argmin yes as well. So actually, one of the tests I did when I was structuring this architecture was I took the Bellman-Ford algorithm and I looked at its components. I said, okay, I need to perform this bound date update, which includes a min operation. So I generated a synthetic data set of vectors that I wanted to calculate argmin on. And I ran a classification problem to see if it's actually possible to do that with an LSTM. And it is possible to calculate argmins on input feature vectors. So you can imagine I had the 32-dimensional feature vector with one of the entries is the min or the max or whatever, and then I perform classification over on those examples.
And you could have used other approaches for that. For example, if there is min max pooling for finding the min and max, and for the argmin, I'm not sure. But, so did you consider other approaches, or was it an obvious choice to go to that?
I think it's important to stress that although we take inspiration from the Bellman-Ford algorithm, we didn't run. We don't assume that what we have at the end is the Bellman-Ford algorithm, and so I didn't. There's a point where you don't want to put too much structure, because at the end of the day, what you're doing then is you're actually just implementing an algorithm yourself. You want to be able to learn the parameters of this algorithm end to end, rather than just going through these whole modular pipelines. And so I didn't look at that part.
Okay. One of the questions I had for your approach is that it's probably depending a lot on the exploration policy and the data creation policy. So you explained that you trained it separately, but do you have an insight of the performance of this? Is it sufficient? Is it a limitation of your global approach? Or?
I obviously perform some evaluation in terms of offline of percentage of coverage of this policy. And it's from memory, it's reasonably good, even in a validation environment it hasn't seen before. But I think it's a limiting factor, and also a limiting factor is that these things are trained so that the exploratory policy and the linkage function are trained independently of the neural plan. And what would be better is actually to train all these things jointly. So the neural planner is receiving, for example, the features from a CNN, but if it wants to make updates to those features, it can't. There's no way to backprop from those features into the CNN. So it'd be better if all of these things were trained jointly in an online approach, but a lot more challenging to implement. And so we chose to decouple these approaches for that reason. So I hope that answered your question.
Yeah, okay, thank you. And I had another question on this is about the orientation of the robot. So you use a topological graph, which is encoding positions, and then you have images which are not panoramic images, which are linked to the direction. And it's not very clear for me how this can work well. Do you have some mechanism somewhere to take into account the orientation of the robot? For example, when you estimate traversability, do you assume that the robot is pointing in the direction of the edge, or it can be a traversability on the edge of your right when the robot is looking in front? Or what? How do you see this orientation?
So obviously, you'd expect this to have the best performance when the two observations are looking at each other. So you have two observations taken and they look directly at each other, and you're calculating the connectivity of that open space, or if there's a wall. But it's true that it could be a real downside if one of the observations is just the agent facing a wall and you can't conclude anything from that. You're obviously not going to have a good estimate. And I think this is where some of the regularities in the graph help. But also, you could imagine that both the observations are looking at the same object. So you can see a sofa in your environment, you can both see the sofa. Perhaps that gives you some information about whether there's line of sight connectivity between your two observations, because you can both see the same object. So they don't necessarily need to be looking at each other, but I think it is a limitation of the approach. Obviously, a panoramic camera would be better, but if you're then wanting to transfer this approach to the real world, you now need to buy a panoramic camera, which is probably not cheap. So.
Well, there are cheap panoramic cameras, but yeah. Obviously, it's good to be able to deal with the robot orientation also. So, yeah, maybe adding some process to deal with that would be interesting. Okay, and I also really liked your contribution for the video game using a local policy for local behavior, and then using this sampling and classical path planning approach. Would you say that the fact that you use reinforcement learning as a local policy changed something on the global complexity of the task in a sense? I mean, if you have a way for local policy to build them manually or using other approaches, would it change anything, or
I think
would it be the same?
Yeah, you can consider that just to be a heuristic. It doesn't have to be trained with RL. If you had another heuristic that can perform point-to-point local navigation, you could use that, and the approach would still function. The problem is that in these complex environments, you don't really even have a heuristic. And so, because you've got so many complex actions, jumping and jump paths, etc., the number of possible actions is enormous. And typically in video games, you do use graph search to search for the right actions to take. And when you've got so many different possible actions, this graph becomes enormous and you can't use it in real time. And so that's why they like RL approaches. But yeah, going back to your point, it could just be some sort of navigation heuristic that just walks in the direction of the next point. And if that's good enough, it would still work with the same approach. So it doesn't have to be RL.
Okay, and last question is on the perspective. So you point to interesting direction, but I was missing a bit perspective on the performance of your contribution. I was mostly on ego map and topological mapping. And what would you need to add? What could you add? What are the main limitations? So maybe you mentioned some of them already before, but what would be the main perspective on improving the two approaches you present?
One of the ideas I had, and I don't know if it would be an improvement, is that when you learn the ego map, you rely on this depth estimate or depth from an oracle, which is a weakness in my opinion, and you also rely on these ego motion estimates. And I think it'd be really interesting to structure the model such that it uses outputs from a neural network for its ego motion, but it doesn't actually have an oracle that's providing what those are, and it uses estimates of depth for its inverse projection, but it doesn't actually have an oracle providing what those are. And so it performs this projection, it moves its map with an affine transform of some values that are predicted by the neural network. And then actually you learn those values through reward. So the idea is you learn the most suitable way to project your features with depth or some value through reward, and you learn what your ego motion estimates are through reward. And because there's a link between those two, there's a link between your ego motion and where features are being projected from one time to the next and the depth you're using them, you could then learn this relation without actually having supervision from an oracle. I don't think it would perform better than the ego map, but I think it's quite interesting. If you could learn depth through interaction, it could be really, really an interesting observation. And then, of course, you're not limited to having an oracle. You don't need the oracle anymore. But I don't think it would outperform ego map, but I think it's an interesting research direction that I thought of after I did the ego map work, but I never explored.
Okay, yeah, I completely agree. So thank you very much for your answers. I will leave the floor to the next member.
Merci, David. So let's continue on video with Kartik. Kartik, you hear us?
Yes, thank you, Cedric, and thank you also, Edward, for your great presentation. So I had several questions before we started your defense, but some of them were well answered in your presentation. Also, some of them came up in the discussion with Elisa and David. So from the rest of the questions that I had, so there are a few which are sort of more on the technical aspects and some which are maybe more generic. So I'll start off with the more technical ones. So in the first contribution that you were presenting, so I understand now that you were, there was some use of depth information, there was some use of the location or the coordinates in creating these maps. But I was wondering, in addition to this, do you think of any other modalities that you could think of which would be useful for improving, let's say, this work?
So the first thing that comes to mind, and I don't have many things that come to mind, is you perhaps could have, if you have a segmentation information about classes, like in the semantic slam like approach, this could be useful to have additional feature maps in your tensor. And in fact, there has been some parallel work that investigates that. I can't remember the name of the paper offhand, but there has been some similar work where they use semantic classes in a map instead of learned features. And obviously that goes back to these, when you craft these modular approaches, you then need to have these semantic classes annotated and you have a predictor that's predicting them. So you could use that modality. Offhand, I can't think of any other modalities that would be interesting. I'm sure there are, but offhand, I can't think of it.
Okay, that's great. But I was also thinking of, let's say in computer vision these days, there's a lot of work that has been looking at in the past, let's say 10, 15 years of other types of modalities from video, for instance, audio. And I know it's not the case in the platforms or the data sets that we've considered, but in the future, do you think there would be use for, I don't know, sort of objects or things that would make some sort of sound where you would capture this information additionally? Such as a bell that rings or and different objects producing different sounds. Do you think that is anything that would be interesting in this domain, or
I think going back to like video game applications, you might have an enemy that's in the environment and it makes footsteps, and so something like that sound is also used to localize this enemy. But I don't know how you would use that in the context of mapping it. That's the
Well, I was sort of more looking at it from the perspective of, the ways certain objects sound could be different based on the distance or what obstacles you have in between, and how many, let's say, rooms down they are further down the rooms. So essentially, as you're approaching, a sound, it would be different in terms of the frequency, the level of the sound that you hear. So you kind of can provide you perhaps cues and saying, oh, maybe you're going the right direction or going in completely opposite direction.
So yeah, I think in that sort of context, they could definitely provide cues. I'm trying to sort of find a parallel of how you do this inverse projective mapping, because you would know the direction perhaps, and you'd know the distance from the amplitude of the sound. So it's obviously it's nearer, it's going to be stronger, and then you could use that to approximately localize it where it is in your frame of reference and map audio features from that sound into your map. But it would be quite sparse in terms of what the signal you're mapping. Here you've got many feature vectors for observation, whereas one sound will be mapped to one location, for example.
That's true. Okay, so in the same contribution that you presented, so I may have missed, there was one graph you were showing that you do in fact need a lot of interactions with the simulator. It was maybe around slide 37 if I didn't mistake, yes. So here, do you have any idea of how many interactions are ideal? You really have to go to these many millions of interactions, or is there sort of a compromise that you can make at a certain point?
I think you maybe you could use half. You have half as many interactions, 600 million. I'm just looking at the ego map curve, so I'm just looking. It seems to plateau at about 600 million. But either way, it's just enormous. Like it's orders of magnitude too much, and that's why it's good to have a fast simulator. But there's no way you could train a real world agent. It's sort of you need it to be under 1 million, or even then it's enormous. There's it's a real thing that you know, it's obviously an active area of research to improve these sort of things. And there are algorithms. Here I use advantage actor critic, and it's not the most sample efficient. And there's PPO, which is a bit more, and there are obviously off-policy algorithms that are even more. So yeah, there's some interesting questions about with different algorithms. Do we, you know, how could we reduce the sample efficiency, increase the sample efficiency? Sorry, with different algorithms, for example. That would probably be a better way to improve this. But yeah, then obviously you lead to other problems where off-policy training with recurrent neural networks is quite challenging because your data is fundamentally off-policy. Anyway, that's another topic.
Indeed. So my next question is on the second main contribution that you presented. So if you could go to slide 51, please. Yeah, so here you were talking about how you created this uncertain graph, and you said that you have two nodes that you were comparing, I guess essentially using a neural network, right? To determine what is the, let's say, the edge weight that you would like to impose between these nodes. Is that correct, my understanding?
It's not, I wouldn't consider it to be an edge weight, because you typically use weights for planning. It's really an estimate of if there's connectivity between two nodes. And obviously that's going to be binary classification over two possible classes where is there connectivity or not.
Right. So here I kind of missed some of the technical details here. Could you say a bit more about this network that learns this estimate, and what is, let's say, is it supervised network? What is the ground truth that you're using here?
So the neural network itself is it's a parameterized function, and it's a multi-layer perceptron. It's nothing complicated. I don't remember the exact number of layers offhand. Okay,
that's fine, but just in terms of the data that goes into it, and
so yeah, as input, there are the feature vectors from those observations, which have been already extracted with the convolutional neural network. And it's the same convolutional neural network that was used for when training the exploratory policy. So it's shared between the exploratory policy and this F-link function. And yes, so the ground truth was calculated by ray tracing on the 2D occupancy grid of each of the simulated environments. And so that's a fairly easy and fast thing to do. If you've got a 2D occupancy grid, you can kind of cast a ray in a particular direction. And obviously the ray, and that ray direction is from the location of the agent and its orientation in the environment up into the location of the other observation. Obviously, if we hit a wall before that, you can just be sure that you've got no connectivity. So that's how we've got the ground truth. We use a simulator to get this information. And obviously at training time, you assume you have this available, and at testing time, you assume you don't.
Sure. Okay, great, thanks. Right, so then actually carrying on from the question or the discussion that you had with Elisa about data sets. So I understood your answer that choosing which environment or data set you want to use depends on the final task that you're interested in. But let's say tomorrow, I have a new student working in this general topic of navigation, exploration. What advice would you give them in terms of where to start? If your goal is, let's say, just exploration, navigation.
So if you're interested in doing these structures in a sort of more general case or for structured approaches?
I guess for structured approaches, yeah, I would say.
Okay, so we share our code base, for example, for this implementation, but there was an extension by some researchers in Korea, I forget their names offhand, that was accepted, I think in Europe last year, where they did comparisons of this approach, another approach from some at CMU, and a few different approaches, and they share their code base, and it's quite a sort of quite a well-written code base that compares different benchmarks. So that's a really good starting point. You've already have the implementations of other algorithms that have been done or re-implemented by these researchers, and I think they compare against a new approach which outperforms learning to plan, for example. And so that's, I think, is a good starting point. It's best to iterate on an already existing implementation because you can spend a lot of time implementing baselines from papers, and so if they already exist, it's best to go to those sort of resources.
Okay, so I have maybe two final questions which are a bit more generic. The next one is a little bit, I wouldn't say controversial, but maybe worth more discussion is in terms of understanding or interpretation of, of neural networks. I know it's not the main topic of your thesis, but it does kind of lead in that way, having used structured models and stuff. So how exactly would you define, let's say, interpretation? Is it that you need to understand, let's say, all the parameters of your model, the majority of the parameters, or how would you actually first characterize as, okay, this is a good interpretable model?
That's a good question. I must say that explainable AI is not really my domain of expertise. Obviously, I created some interesting visualizations that do explain some of the reasoning process of the agent. And I think being able to visualize some aspects is a sort of criteria for explainability. But always, I think inevitably with these end-to-end approaches, you're going to have some aspects you cannot explain. I think that's inevitable. So I don't have a really good answer for that. What would be my most, what would be a criteria? Like even in the case of the baseline recurrent agent, you can take its hidden state and you can do some visualizations with a dimensionality reduction algorithm, and you can learn some intuition about how the policy behaves under different conditions. So I think often a lot of this information is there. It just, you need to go and look for it, in fact. And so obviously adding structure makes it easier to do that because we know that we've added an attention mechanism and we can visualize it. But I think, yeah, as I mentioned, a lot of this information is there. And one of Christian's other PhD students has been working on explainable AI, and he took my baseline recurrent agent and made some interesting visualizations with it and showed that there is other information there that can be used to get a bit more of an intuition about how the policy is behaving internally. I don't have a better answer than that, I'm afraid.
No, I think that's a very good starting point, and I know it is not the main focus of your PhD, so it's not a problem at all. So maybe just to wrap up, like, okay, so this is all great with looking at one agent exploring an environment, but would you see then? Do you think one of the next steps is to perhaps introduce multiple agents into environments such as this, agents who maybe are collaborating with each other and trying to find the goals jointly, or maybe they're even competing? I mean, in games, this can potentially be an interesting thing, but do you think your approaches would naturally extend to this sort of multi-agent setup, or do you think there's still a big gap that needs to be filled before you go there?
Obviously, again, yeah, multi-agent RL is not really my domain of expertise, but let's consider the ego map example as a reasonable example. So there you could have a shared global map, and you have many agents that are exploring the environment, and they're each projecting their feature vectors to a shared map, and they're all able to query the shared map to improve their exploration or reasoning process. So I think in that case, you could extend it to a multi-agent setting. It'd be very interesting to see what that would lead to and what tasks you'd need to define in order to test that sort of hypothesis, because these sequential collection tasks maybe make sense for a single agent, but would they make sense in a multi-agent setting? I'm not sure.
Okay, cool. That's very good. So thank you again, Edward, for your great work and wonderful presentation. So with that, I give the floor back to Cedric.
Merci. Let's go back. So with Christine.
Yes, thank you, Mr. President. So first of all, congratulations for this very, very nice presentation, and thank you very much to the advisors to invite me to participate to this. It was the opportunity for me to better understand deep reinforcement learning, so thank you very much. I must confess that I have learned a lot of things, but there are still things that are kind of magical for me. But I think I'm getting closer to really understand what's going on in deep reinforcement learning, so thank you very much. I had a question about explanations, but already has been asked, but still, so I won't ask the question, but just say that if you want to have robots in an environment with humans, it is necessary to have some kind of symbolic reasoning possible to explain, because humans will ask, why do you go there, stupid robot? And the robot must be able to answer and to justify it. So in your example, I was wondering, is it just a nice illustration, or do you always have this kind, in all cases, you always have a kind of explanation, a kind of interpretable visualizations of the behavior?
So in the paper for Ego Map, so here I show an example task. That's just the slide I showed before. So where we're looking at this attention distribution and seeing whether it's querying this object. So in the paper I show another visualization for another task where the agent has to find an object and then return to its starting point. And there we see the agent attends to its starting point. There's another object at the starting point it needs to return to. So in these more complex tasks where you need to go somewhere and go back and collect a sequence of items, we see that the agent is performing this querying because it's looking back at its memory to where it's seen some things. But in, say, a labyrinth task where you just have to find an exit, I made similar visualizations that you don't really use, the agent doesn't really use the map in the same way because it doesn't need to query for previous information in the same way. It's not querying for an object it's seen before, it's just using the map maybe as an exploration, for exploring, and perhaps there's some path planning that's being conducted. I need to investigate it. But it's not performing querying, it's not selectively searching for certain objects because that task isn't really reliant on those. So it depends on the task. I think as tasks get more complicated, we would see the agent using the map more and more because it need to query.
Okay, thank you. And then I have a second question, and this will be my last question. I think we are getting short of time. And the question is also for Christian, because I'm sure he wants me to ask the question. So this is on slide 57. Next one, but let us start with 57. Okay. Here you solve with this chart what I would call a static problem. I want to be sure that this is the case. So you give to Dijkstra the graph with on every edge the probability that the edge is present. That's right?
No, so
Okay.
the first example one, we have our nodes, we've estimated connectivities with the neural networks, their values between 0 and 1.
Yeah.
And then we threshold those values with
threshold.
threshold.
Okay, and the second one is okay, right. But these threshold or cost, they are static in the sense that you compute that at the beginning, and then you run Dijkstra, you obtain a path, and that's all. And you don't during when your agent is moving in the environment, he is collecting new information, and these probabilities are updated. And
No. So the graph is fixed.
Yeah,
The
so
graph-
that is what I call a static.
Yeah, so the static graph.
Static stochastic problem. And well, that's not fair.
No, so in
From my
both cases the graph is fixed. We don't have the update the graph in either case.
Okay.
The graph is fixed, and we perform
But
planning.
then you compare, I think this is on slide the 59 maybe, or 58, yes, this one. Then when you give the results of your neural approach, you are not in a static setting anymore. And your agent has new information.
I agree with you as new information, but we don't use that to change the graph. The graph is fixed from time step 0. The graph is fixed.
Yeah, but the probabilities
No.
on the edges, when your agent is moving, he will see that, well, actually, these probabilities, you can see them as random variables, and at some times, some of these random variables get realized. And then you know that there is a connection or there is no connection. And then you can adapt your path.
I agree, and we could have looked to implement that approach, like updating the graph in an online system.
Yes.
However, the graphs we produce here are static, and they remain static for the entire sequence of interaction between.
So your neural line, you never update the probability.
Not based on this information. No, and that was actually an extension I worked on.
Why?
So
Why don't you do that?
so the idea was that we generated this work was meant to be part of an online work where we would also update the connectivity online, and I never got it to work. I spent a year and a half. And part of that research work was this contribution, this neural path planning algorithm, which we submitted to a conference. But it was only a small part of a much larger work, which I never got to.
Okay, so just to be sure that I understand correctly, you mean that when your agent is at some point and he really see that he cannot pass, you don't update the probability to set a zero on this edge?
So not in this information. Not in this implementation, it's completely static from the first time steps to the end of the interaction with the environment. It's a real limitation, and the idea was that this was a step in the right direction. We made a publication about it, and it was going to be online, being updated on the fly. And whether the problem is too difficult or it's the limitation of my capabilities, I never got it clear. And it was a bit of a sore point actually during the whole thesis. This kind of, the fact that one day we realised this is never going to work. We were just,
Okay. Because my suggestions was to experiment an architecture where you do use neural networks to learn these probabilities and update them, but for the path planning problem, simply use a multi-stage stochastic optimization problem. That would be much simpler to solve. I think it would be interesting. For the next thesis. Okay, so I think I'm going to stop here because. But thank you very much.
Thank you. Merci. So before giving the floor to the supervisor, I can ask some few questions. You have plenty of questions, so it's a bit difficult for me to find some original one. But anyway, so first of all, I would like to thank the supervisor for this invitation. It was really pleasant for me to be here, to hear you. It was really interesting to see your work. Just one question about the first contribution. When you modelize your problem with Doom. So you mentioned that you can modelize plenty of sensors, so RGB, depth sensor, LiDAR sensor, segmentation also, but I didn't see any results with other interests than RGB. You use only RGB, for example?
yeah, so apart from in the ego map contribution where we depth as well for this study, no, I didn't use any, and the reason is because it's quite interesting to do navigation just from RGB. It's quite an interesting.
Yes, but yes.
You would assume that information is going to be available when you go to a new simulator or when you transfer to the real world. It might be the case that you don't have that segmentation available. But you can segment in Beeching, for example, you can segment classes. Different objects can be segmented as possible to do it. But you obviously assume that down the line, that information is going to be available in another simulator or the real world. Might be the case.
So in your experiment, you use only RGB plus D?
RGB plus D.
Plus D.
So
How do you merge RGB and D in your algorithm, in your architecture?
okay, so for the baseline, it's just another channel in the input.
Just a channel.
It's just another channel, so each pixel has got a depth value, and it's the actual depth in the game or the simulator. And then for the ego map, in addition to being part of this observation, I showed just here RGB, but there's also the depth.
Mm-hmm.
It's also used for this inverse predictive mapping, so going from screen space to the world space. And I think that's actually the weakest part of this approach. As I mentioned earlier, it'd be better if we were performing prediction, or there are noise on the RGB, but it's real world sensors, and actually going to be noisy, particularly depth sensors. Kinetic sense.
Yes, I see. If I want, just want to navigate in the environment with simply navigate without the obstacle, I think it's better to use LiDAR. No, in your opinion, or depth, or just RGB, because with RGB you can also extract depth thanks to mono depth CNN, blah blah, something like that. But in your opinion, what kind of sensor should I use?
It depends. I imagine depth is quite good, but it also depends on what the environment is. If the environment's cluttered and there are objects on the floor that are quite small that you need to navigate around, then visual information from an RGB camera might be useful, so you can learn to classify the objects and say, okay, I don't want to walk over, it's a cat or whatever. So in that case, it really depends on the main application. But if you're in a factory, and it's got a controlled environment, you know that there's, we say, rubbish from workers working on the floor, and probably depth sensors are enough. So it really depends, I think, on the domain of that.
In SLAM Vision SLAM, we show that it's better to use panoramic images for navigation. In your opinion, is it also the case with deep learning? So if I use a non-directional images for navigation, so I have the same task, I use the RGB classical perspective images or omnidirectional images.
I think omnidirectional is inevitably going to be better because it provides more information about the environment. You don't need to turn your robot to look to the right of you, you've got that information.
And do we have to modify your architecture, the deep learning process, by taking into account these kind of images?
So in the case of EcoMap, just propagate it forward all directions, as long as you've got the depth and that's the depth. And in the case of what I call TopoMap, it's a neural path planner, I think it actually improve the connectivity estimates. So there was another question previously that you're assuming your agents looking, your two observations are looking at each other, and if you've got a panoramic camera, that's always the case that one angle is looking at the other, right? Assuming there's a wall. So I think having those sort of cameras will inevitably improve the performance, and it's feasible to incorporate them in.
On your experiments, you didn't mention the reward function. The reward function is really important. So this reward function has some fixed parameters. What is the influence of these fixed parameters if I modify a little bit these parameters?
So it changes enormously the result of your course. So for example, often people perform point-to-point navigation in these photorealistic environments, and so at every time step you're given a point location to navigate to in your frame of reference, which is a great source of information. And then also the reward function is your improvement in distance to that location. And you get that at every step. So it's a very, very dense reward system. And so if you were then to move that to a sparse reward setting where you only get a reward when you encounter your target location, you get reward much less frequently, and inevitably that's going to mean you're going to have to interact more with the simulator because you have to rely on essentially random actions at the start to pump into your reward. So the Beeching settings were like this. They were sparse rewards based on objects because I think it's better if you can get away with doing this, and you can do it, it's better to do that because you're really just defining the task you want to do. You're saying when you get to this object, you get a reward. Through reinforcement learning, you're going to have to work out the best sequence of actions to get to that reward. And as you start handcrafting and tuning, it makes it easier for the training, but there's the human that needs to define this complex reward function. But yeah, so in answer to your question, it changes enormously the difficulty of the problem and also the performance of the converted process.
Okay, just one general question. During your acquisition, you compare your deep learning practically with classical SLAM model. The main advantage of SLAM is it works in real environment, even in dynamic environments. It's not really the case for the moment for your approach. So, in your opinion, this is what you mentioned in your perspective. How can we break this gap between simulated environment and real environments for using RL?
I'll put the idea of dynamic environments to the side at the moment. Let's just think about static environments because it's a bit more simple to sort of make a comparison.
Sure.
And so in that case, there are some examples, and there are some examples from Christian's team where they perform simulated transfer of a policy. You take a scan, like we put a scan of the upper level of our building, and you train in simulation of that scan, and then you take policy that has been trained in a simulation and you put it on a real world robot. You have to do some adjustments of your camera, intrinsic parameters in order to sort of make it as close as possible to your simulation. But then you can find that these policies do transfer reasonably well to a real world environment.
Mm-hmm.
And obviously depends on some limitations of what your actuators are like in your robot. And if you can model the noise that those motors have in the simulator, so often you can model the noise events, so drift or some random noise to those actuators. So that has been shown that you can get kind of comparable performance to SLAM, and there's a paper by Guillaume in Christian's group that showed you get comparable performance to SLAM with an end-to-end learning approach to transfer from the same simulator to the real world. I think it's a bit more tricky, and I'm not sure if go back to the paper, I'm not sure if they did a comparison where they train in separate environments and then transfer to a new one. So he is just nodding, so apparently there is. I don't remember the conclusions. I think okay. And so that's sort of to do with static environments and end-to-end approaches can be transferred. And I think if end-to-end approaches can be transferred, if you can alleviate some of these issues with maybe your depth predictions aren't very good. If you can improve that, then perhaps some of these ego map or like approaches can be transferred with a reasonable way of performance as well. Dynamic environments is a bit challenging, and it's not really my domain. But yeah, clearly the ego map it doesn't deal at all with dynamic environments. It doesn't have any assumptions about the fact that the features it maps could be moving. So yeah, it's an interesting question. I know that in the Chroma vehicles team, there's CMC dot, which they use for mapping. It's a very similar approach actually. They use for mapping predictions of pedestrians into a similar sort of top-down map with a Bayesian of occupancy grid, and they use those for tracking pedestrians as a more dynamic environment. So perhaps there are sort of research directions related to that. But again, it's not really my domain.
Yeah, okay, thank you. So I think I understand. So you have to approach your supervisor, starting from Beeching.
Thank you, Mr. President. So I don't have any questions. I know it worked. So I just want to thank the support that we have for the studies. It's great support for the freedom that gave us during the PhD. I also want to thank the co-advisors, Olivier and Christian, for the expertise that you bring us before. Obviously, everyone for the great job and excellent job, I would say. So your ability to balance between the diversity of the opinion, the advisory board. So that was great. I appreciate it a lot. Thank you very much.
Merci, Gilles. President. Yeah, I will try to be as short as Gilles. Now, really, I would like to give some thank you to first the jury, the reviewers for the job, and for the jury for the work. But probably my first thanks is to you, Edouard, for so great work, nice presentation today, but for all these years, and to Christian to make possible this work, this subject, and as everyone knows, Christian is the real main director of this PhD, and that it was a real pleasure for me to work with you, and probably for me to discover such a domain of
deep RL, deep learning, but apply planning and robotics planning and navigation. I think that we make a good step to connect to domains. And so, thank you for this. And also, I would like to underline that I was surprised by your capacity of work and your ability to manipulate complex concept of architecture, and in the meanwhile to develop, to make so much experiments, to develop tools as the Godot framework. That's very impressive, and it was a very great job. So thank you again to you, and thank you to my colleagues for this work.
Merci Olivier. Last but not least.
Thank you, Monsieur le Président. Well, it worked a couple of years past. You're now almost a doctor. It was a pleasure to work with you. I have so many things to say. I will make it less short than what Gilles and Olivier said, but I try to be as short as possible. So yeah, we time goes back to when you were when you did your masters in Saint Etienne and we were able to recruit you. I think a couple of people were not so happy about this. People here right now.
I forgave you.
And yes, it was a great time, and I would like to give a couple of impressions I had having you in the team. The professionalism, for example, you showed during the work, and in the work itself, in science, we'll come back to this later, but also in everything which is around. Organizing meetings, coping with 3 supervisors, which couldn't be more different scientifically. One example is the first presentation you gave. We like 2 rehearsals, like we do for every student. I mean, your first presentation was not a mess, which is normally always the case. I mean, it's a really difficult task to do a PhD, and your first presentation could have basically been your defense. So it was really well done. I also like your humbleness, and in light of what you do, which is excellent work, you're very humble, you're motivated to learn, you have a scientific démarche, whatever it means in English, in a sense that you really want to know how do things work, why do they work, if I read a paper, if there's some nonsense in there, what are the core contributions, let's get down to the real science behind it. And that's not always the case. We would like to point out that's really good. Before I come back to you, I'd like to give 2 minutes on the history of this thesis also, because there are a couple of things which you didn't present and which were part of the thesis, no. But just for the jury members and for the people who are still following us online, the history of EgoMap, for example, because there are a couple of things which are not known. So EgoMap was done pretty quickly during your masters already. At this time, projective geometry was not yet used in reinforcement learning. And one of the sore points in the community was that, well, the paper was refused twice. Probably still remember the top level conferences. And why was that? Because we were at this point still working with Wisdom, which is not the problem for supervisors, but the community and the reviewers said, well, you're not working in photorealistic environments, you didn't switch to habitat like everybody else. But everybody else was basically doing really easy reasoning tasks, point goal, going from one point to the next. Whereas we were asking good questions, you were asking good questions on how can we make agents map, what tasks we need to invent to make them map from reward. And sometimes the community is more impressed by nice images and photorealistic environments than by the scientific questions. So that was a sore point, but actually it turned out well. I just want to mention that a variant of these tasks was then proposed as a benchmark in Europe's 2021, I think. And yeah, all your papers are widely referenced in there, all your footprints are in this benchmark. So you clearly had an influence, EgoMap is in there. Yeah, so your influence goes way beyond your thesis. Your work has been reused by other students, also in the team, for example. After you used your explorative policy and EGOMAP will be reused in other. I'd like to go back quickly to what Elisa said. She said, and she's right. It's completely right. She said, I was reading this thesis, things look very complicated and I thought this will never work. But they magically do. Well, it's not magic. So what Edward did is not magic. He just had this, well, that's one of his strengths, finding out what baselines can do and then find the minimal steps to go ahead. What do I need to add now? What do I need to do to make it work? And do the right plan, going from the simple baselines to the complex ideas. And that's one of the things a good researcher in the deep learning area actually needs. That's probably one of the most important things that you have to. So that's really good. Yeah, I have lots of other remarks, so I will control it. I wish you all the best. I think it's no secret that you started a tagging phase. I think I can say that you tweeted it anyway, so I think it's done. So Edward started the tagging phase, and I think he is right now in, at least in my opinion, the one area in machine learning, deep learning, which is probably one of the most promising areas. He's working on, well, you showed it in the future work section, making language models and foundation models grounded through interactions in robotics, and that's an extremely promising area. And I think Hanging Face chose very well to hire you. I wish you all the best, and I think you'll hear again.
Merci. Merci, Christian. Je pense que c'est délivré. Ah, pardon. Y a-t-il un docteur dans la salle qui souhaiterait poser des questions? Oui, on va faire un problème. On va remonter pour délibérer dans mon bureau et les deux collègues, donc Kartik et David, vous vous connectez sur le lien de tout à l'heure du jury. À tout de suite dans 2 minutes, je pense, à peu près.
Oui, à tout de suite.
Yes, sir.